Alright everyone, I want to start this video with a warning. It's going to be longer than usual because we're going to do a problem that involves many steps, as you can see. So we're given this system on the left, and the values for the constants, masses, and the forces are given in the table. We're asked to find the force response, rather, x sub 1 and x sub 2. Alright, so the first step is simply to find the governing equations. We've done this many times before, so it shouldn't be that big of a problem. Step number 2 is to calculate the natural frequencies by setting the determinant equal to 0 of the stiffness matrix minus the natural frequencies squared times the mass matrix. After that, we're going to calculate the mode shapes. Again, we've done this before, it's not too complicated. With the mode shapes, we're going to assemble the P matrix or the modal matrix, and then we're going to calculate P star. After that, we're going to calculate the normalized damping matrix Z, and its diagonal elements can be used to find the damping ratios. From there, step number 6 is to find y sub 1 of t and y sub 2 of t. So in many textbooks, y sub 1 and y sub 2 are called the modal coordinates, and from those we can revert back to step number 7, the actual coordinates of the original system. So as you can see, it's pretty involved, and we're gonna start to get to it right away. Okay. So what I'm going to do is, first of all, make some space, and I'm going to push this down as we go. Alright, so the governing equation, we're simply going to write it out in matrix form directly. So here we have number 1, the mass matrix, diagonal, the damping matrix. Mass number 1 only has C1. It's symmetrical, so we get this value easily. And then we have C1 and C2 attached to the second mass. And then the same thing for the mass matrix, the stiffness matrix rather. Alright, so in the right hand side, the vector holds the amplitude values for the external force. So we have 1000 and 0, and then we have the cosine of the excitation frequency 30t. Okay, we're going to substitute in the values. So we're going to get 10 to the second power times 10, 0, 0, 3. This time we're going to take 10 to the third power out, and we'll be left with 2 minus 2 minus 2, 4.5, because it's 2000 plus 2500 times the velocity vector. For the stiffness matrix, we're going to keep out 10 to the 5th power, and we're going to get 4 minus 4 minus 4 and 9. times the displacement vector. All right, so that's step number 1 complete. We're going to go to step number 2. Oops, do this guy out. Sorry about that. Okay, so we are going to take the determinant of the stiffness matrix minus the, I actually made a mistake here. Should be the natural frequency squared. In any case, we're just going to use the lambda notation. I'm sorry, I made a mistake. I had to write the stiffness matrix here rather. 4 minus 4, 9. It's a 2 here. That's equal to the determinant of 10 to the 3, 400 minus lambda minus 400 minus 400, 900 minus 0.3 lambda. And we want to set that equal to 0. Now the determinant, we take this product times this product and we set it equal to 0. The 10 to the third power will simply disappear by dividing both sides of the equation. So if you do that, you're going to have 400 minus lambda times 900 minus 0.3 lambda minus 400 squared equal to 0. And if you solve this, you're going to get lambda values of, in ascending order, of 208.9154 and 3191.0846. Okay. Therefore, the first natural frequency is equal to the square root of 208.9154. That's 14.9 0.4539 radians per second, and second natural frequency is equal to the square root of 3191.0846, and that gives us 56.4897 radians per second. All right, step number 2 is complete. We're going to go to step number 3 and find the mode shapes. I'm going to bring this guy down. So the mode shapes are given by this guy is this guy. Yeah. So we're just gonna take it's 10 to the third times 400 minus lambda sub I minus 400 minus 400 and 900 minus 0.3 lambda sub I. Okay. Times the mode shape vector 1 and r sub I is equal to 0, or the 0 vector. Okay, so for I equals 1, we have 400 minus lambda I times 1 minus 400 r sub I is equal to 0. And we got that by multiplying this line by this vector. Okay. Notice again that the 10 to the third power disappears because we simply divide both sides by it. And then we get minus 400 plus 900 minus 0.3 r sub I, rather. .3 lambda sub I. All of that times r sub I is equal to 0. Both of these will give you r sub 1 equal to 0.4777. Now, if we substitute let's say I equals 2, and actually here I wrote it with the sub I notation, so I'm not going to write it again, and you will get that r sub 2 is equal to minus 6.977. Okay. So we're going to write our mode shapes before we go on to the next step and assemble the P matrix or the modal matrix. So we have 1 and 0.4777, and the second mode shape Okay, so we're done. Let's go on to the next step. We're getting there. Even a little bit more. Okay, so the P matrix is equal to P sub 1 and P sub 2. So that's equal to 0.4777. Okay, now P star is equal to the P matrix. So I'm just going to copy and paste it. Transpose times, actually the transpose is over here, and then the mass matrix, which is this guy over here, okay, minus 1/2. Now if you're using a calculator or any other kind of system to do this for you, which of course you are, the angles must be set to radians. Otherwise this won't work or shouldn't work. Okay, so the P star matrix we're going to write it out. P star is equal to, and you get 0.306, actually 0.0306, so 0.0306. Okay, so step number 4 is done. We're going to go to number 5, in which we're going to calculate the normalized damping matrix. Okay, so is equal to P star. We're going to get lazy again. P star transpose times the damping matrix. The damping matrix is this guy over here. Okay, so and then the P-star matrix again. This is known as normalization. And what you're going to find is, or should find rather, is a diagonal matrix like this, 1.0446, 0, 0, 15.95554. Okay, so there's a note right here. We're going to calculate the damping ratios with the diagonal elements. And the natural frequencies. So the first one is 1.0446 divided by 2 times the first natural frequency, which was 14.4539. 14.4539, and that's 0.03614 unitless. So the second diagonal element is 15.9554 divided by 2 times, I think it was 56.4897, and that's 0.1412. Okay. Do not despair, we're almost there. Okay, so we're going to calculate or transform the force vector or the amplitude vector of the external force into modal coordinates. So we'll call it f sub y. And we're going to use the P-star matrix again. And multiply it by the amplitude vector, which was 1001. Yeah, that's right. And that gives us 30.6 for the first one and 8 for the second one. Okay, A is done. Now let's calculate the modal amplitudes. And so we get 30.6 divided by the square root of the first natural frequency, 14.4539 squared, minus the excitation frequency, which is 30, all this squared, plus 2 times the first damping ratio, which is 0.03614, times first natural frequency again, 4539 times 30 squared, okay. And so y1 should give you 0.03614 4, 4, 2, 3. Let's calculate while we're at it the first angle, theta 1. We're going to use the a tan 2 function. So that's 2 times 0.03614 times the first natural frequency times the excitation frequency, 30. All of that divided by and that should give you 3.0942 radians. By the way, this isn't unitless. It's just that it's not stipulated in the problem what the units are. Y2 is equal to 8. Second natural frequency, which is 56 point, I'm not sure, 4897, 56.4897 minus squared, 30 squared, all of that squared, plus 2 times the second damping ratio, which is 0.1412, times the second natural frequency, times the excitation frequency, all of that squared, and okay, so that should give you 0.003418. I'll remove the units because we're just not going to bother with that here. Okay, now we're missing the second angle, and that's equal to a tan 2 times 0.1412, the first damping ratio, times the natural frequency, and that should give you 0.2060 radians. Okay, so that was B and C combined. Now let's do D. Yeah, let's just start here. We can simply write y1 of t is equal to capital Y1 0.04423 cosine of 30t minus 3.0942, and y2 of t to 0.003418 cosine of 30t minus 0.2060. Okay. One last step. So we need the P star matrix. We have a diagonal amplitude vector. I just want to correct my notation. Which is fine, so leave it as is. The first one is 0.04423, 0, 0, and 0.003418. Is that so? Yes. Cosine of the first angle, which is 3.0942, sine the second angle, don't forget to put your calculator in radians, of course, and I'm running out of space. Almost. And we're there. We have arrived. The answer is minus 0.001325 times the cosine of 30t plus 0.4 times 0, 6971. I apologize, my zeros look like 6 sometimes. Times the sine of 30t. And minus 0.0008321 cosine of 30t plus or minus 0, 5 times 0, 8489 sine of 30t. We're going to highlight our answer. And we are actually done. So thanks for sticking around. I know that this took half an hour, but if you get this on the test, it's probably going to take you just as long. If you want to have the PDF worksheet, it's in the description below. Thanks for watching.